Hello dear participants, now we are starting lecture 18 of micro irrigation engineering subject. Lecture 18 deals with variable displacement pumps. These pumps are more relevant to micro irrigation systems. Here in this particular lecture, we will discuss about what are the different parameters which deals with variable displacement pump. We will discuss more about centrifugal pump and the most important characteristics regarding selection of pump and how to match with the available groundwater or well data, so that we get best performance out of the pump. So, we will discuss in this lecture. A variable displacement pump, in this pump discharge is inversely related with pressure head. So, as pumping head increases, rate of discharge, or we say capacity of the pump decreases. So, variable displacement pumps require greater input power at low head because of increase in discharge as the pumping head is reduced. When we talk of variable displacement or variable pump, discharge pump, there are important specific parameters, and one of the important specific parameter is specific speed, and specific speed is often used as an index to operating characteristics of pumps. It has interrelationship between speed, discharge and head. Originally, this index was developed in FPS unit, and it is the speed in revolution per minute at which a theoretically and geometrically similar pump would run if proportioned to deliver 1 gallon of water per minute against 1 foot of total head at its best efficiency. A specific speed can be related as speed of the pump into square root of discharge Q divided by total head to the power 3/4. Now, this same relationship it exists whether in FPS system or in metric units which are used. Only thing that the discharge in case of FPS unit it is in gallons per minute, and in metric system discharge Q is in meter cube per second, and head is expressed in feet in FPS system, and in metric system it is expressed in meter. There are affinity laws when we deal with the pump. These affinity laws are related with total head, discharge, brake horsepower, width of the impeller, speed of the pump and diameter. They are interrelated, and changing these parameter, the operational characteristics of the pump also changes. And these are beneficial when we understand fully, they are beneficial to alter the performance of a single pump to match the system performance under different operating conditions. So, there exists definite relationship, and this relationship can be given when we are considering the change in speed of the pump. They can be related as q by q naught equal to n by n naught equal to square root of the ratio of h by h naught and cubic root of p by p naught. So, here q refers to the pump discharge, q naught refers to original pump discharge, n and n naught these are the pump speed, but n naught means that is an original. Similarly, h refers to the head, and when I say h naught, it means it refers to original head. Now, if we are considering the effect of change of the impeller diameter, then the change in the diameter means d and d naught when we are considering. So, q by q naught equal to d by d naught. So, d naught refers to the original diameter of impeller and d refers to the change in the diameter of impeller. Pump parameters. A pump operates most satisfactory under a head and speed for which it is designed. So, operating conditions should therefore be determined as accurately as possible to select pump well adapted to the particular condition of operation. Now, we are supposed to know different terminologies when we are talking of different types of pumps. So, these terminologies are capacity of the pump and suction lift. Capacity refers to the total volume of water pumped per unit time. It is generally expressed in liter per second. Suction lift exists when source of water supply is below the center line of the pump. Now, here you can see this diagram. In this diagram, what you see here, this is the source of water and pump exists below the source of water. So, up to the whatever the level of water exists from the center line of the pump, this particular term is known as static suction head, and then the water lifted by the pump to the desired head, this from the water level of the source to the delivery side of the pump, that is the center of this diameter of the delivery side of the pump is total static head. So, total head is known as static discharge head. Now, if normally this kind of condition it exists in centrifugal pump, where the source of water is located at certain depth below the ground level, this pump is kept at the ground level and then the water lifted from the source at a particular level to the center line of the pump. Here this is a static suction lift, this was a static suction head. So, this is static suction lift, and then from the center line of the pump to the delivery side of the pump, this part is known as static discharge head. So, static discharge head plus suction lift give the total static head. Now, these terms are very important while we are deciding the total head of the pump. Now, these terms are again shown here. So, this already I have explained in those two diagrams. So, static discharge head, total discharge head this has been explained. Now, total discharge head, when we say it is the sum of static discharge head plus friction and exit losses in the discharge pipeline or delivery pipeline plus velocity head and the pressure head at the point of discharge. Total static head, this already I have explained you in that particular diagram. So, now it is clear. What is friction head? The friction head is equivalent head expressed in meter of water required to overcome the friction that is caused by flow through pipe and pipe fittings. Pressure head, it is a very commonly used. What is a pressure head? The pressure head is expressed in meter of water in a closed vessel from which pump takes its suction or against which pump discharges. So, H P equal to P over W. Now, H P is the pressure head in meter, P is the pressure inside the vessel which is expressed in kg per square centimeter, W is a specific weight of water in kilogram per cubic meter. So, velocity head it is the pressure expressed in meter of water required to create velocity of flow, which can be given by h v equal to v square by 2 g, and then the v is the velocity of water through pipe and g is the acceleration due to gravity in meter per square per second square. Static suction lift, it is static suction lift is the vertical distance from the free suction water level to center of pipe center line of the pump. Total suction lift, already I have explained in the previous slide that the sum of the static suction lift plus friction plus intense losses in the suction pipe. Suction head exists when source of water supply is above the center line of the pump, as is usual case in turbine operated pump. Total suction head, already it is explained, but once again I am reading here the vertical distance from the center line of the pump to free level of the liquid to be pumped minus all frictional losses in suction pipe and fittings plus any pressure head existing on suction supply. NPSH, in short form we say it is a net positive suction head. Total suction head determined at the suction nozzle connected to pump center line minus the vapor pressure of water at pumping temperature, both are expressed in meters. In pumping of liquid, the pressure at any point in the suction line must not be reduced to the vapor pressure of liquid. The NPSH is a characteristic of pump and it is usually furnished with pump characteristic curves. So, this is normally supplied by the pump manufacturer. Now, when we are expressing the total components, so maximum practical suction lift of a pump is expressed by the maximum practical means this is expressed as the atmospheric pressure minus frictional loss H f minus saturated vapor pressure minus net positive suction head of pump including losses at the impeller and velocity head minus F s, that is a factor of safety which is usually taken as 0.6 meter. So, maximum practical suction lift of a pump for operation of a centrifugal pump without cavitation, the suction lift plus all other losses must be less than theoretical atmospheric pressure. Normally, a practical value it is taken as 6.5 meter. So, normally 6 to 7 meter is considered as a maximum practical suction lift of pump. A centrifugal pump is a rotary machine. It consists of two basic parts, rotary element or impeller. There is a secondary element or casing. So, impeller it is a wheel or disc mounted on shaft and provided with number of vanes or blades, usually they are curved in shape. Vanes are arranged in circular array around the inlet opening at the center. In some pumps, a diffuser consisting of series of guide vanes or blades surrounds the impeller. Impeller rotating inside closed fitting case draws in the liquid at the center and by virtue of centrifugal force throws out liquid through an opening at the side of the casing. So, when this impeller it gets the drive from the shaft, from the motor or from a engine. So, what it does when it rotates, it brings liquid and then throws out this particular liquid in the side of the casing. This is the way then water it comes out of the pump. You can see here this is a volute type of the centrifugal pump. So, these are the impeller vanes, this is an impeller and this is the impeller vane and this is a eye of the suction and this is this particular device is an impeller. So, when it revolves, this revolution is given by the pump the motor and then when it revolves. So, it brings the liquid at the side and by using the centrifugal force the water comes out of the pump. In case of hydraulic line underlying principle is the design of impeller is production of high velocity and partial transformation of this velocity into pressure head. Now, diffuser type of arrangement is the another kind these impeller it has got diffuser types of vanes. So, water it comes in the periphery of the impeller and that is creating the pressure and then water comes out of this. So, this is the another arrangement of the guiding vanes of the diffuser type of vanes which are causing the water to come inside the casing and then it throws out of the pump delivery ends. You can see the animation that it shows the how the water is being taken by diffusion the volute type of spring vane. So, a pump is classified it could be on the basis of the energy conversion, that is volute type or diffuser type. It can be classified on the basis of the number of stages, it could be single stage, multi stage or it can be impeller type, it can be open, semi open, closed. So, when we say number of stages, single stage or multi stage means we are considering the means whether how much pressure we want to create, pressure head we want to create, or when we are dealing with the open or semi closed. So, we consider on the basis of the quality of water. Now, it could be the another way of classifying is a single suction, double suction, construction of casing. It could be vertically split, horizontally split, axis of rotation. It could be horizontal rotation or vertical rotation about the axis, or it can be the drive, that is a direct drive, or it could be a geared type of drive it is given, or by using the belt drive. So, there are factor for selection of pumps. These factors influence the selection of pumping set. The requirement of irrigation water by the crop to be irrigated, this is one parameter. The another one is yield of the sources of water. So, these sources of water could be open wells, it could be stream, it can be river, it can be pond, means that could be the source of water, and how much it can give water. Availability and cost of the type of pump, and then type of energy we are using. So, discharge capacity of the pump by considering the crop water requirement is given by Q equal to 27.78 into A y by R into T. Now, Q is the discharge of pump in liter per second, and then y is the depth of irrigation, T is the duration of pump, A is the area of the crop to be irrigated, and then the T is the at what interval, irrigation interval, rotation period we need to give irrigation. Now, a very important part is matching of pump with well. So, first we are required to construct the discharge head characteristics or discharge drawdown characteristics of well. A typical behavior of head capacity curve of a well is given by you can see here the discharge is shown in liter per minute, and then head is given meter. So, this is the behavior of the typical drawdown discharge characteristic curve of well. Now, we need to match the pump characteristic with this particular well discharge drawdown curve. So, pump characteristic curve also called performance curve, and it shows the interrelationship between capacity, head, power and efficiency of a pump. And then it helps in pump selection which is best adapted to a particular condition, and then thus it obtains relatively high efficiency with low operating cost if it is properly matched or best operating conditions are satisfied. It is usually to plot the head, the power input and efficiency on ordinates and capacity in the FCSA at a constant pump speed. Now, we can see here these are the different curves. So, when we are seeing that head capacity curve, so the capacity practically it is a discharge which is plotted in x axis and this is a head. So, for different speed the behavior of the head capacity curve it look like this. Up to certain discharge it is increasing the discharge the head with the head is increasing, but after certain speed it reaches to a particular value, then it start decreasing. However, the speed causes higher head, it causes the meeting the higher head at higher discharges up to certain value. Then efficiency discharge curve when it is being plotted for different RPM of a pump. So, what we see here that as the RPM increases, there is always increase in the efficiency of the pump with increase in the discharge line, but after certain discharge then it starts efficiency start decreasing. The brake horsepower and discharge relationship, what we see here, as the RPM of the pump increases, the brake horsepower of the pump. It also increases with the increase in the discharge, and there is it exists a linear relationship. The another point is pump operating point. So, the pump particular head, that is H, and discharge Q combination at which pump is operating is the pump's operating point. So, what you are seeing here, that head is plotted in the ordinate, and then discharge capacity of the pump, it is plotted in the abscissa, and then when we are plotting this graph. So, this is a, when you are seeing a typical well drawdown curve. So, there is a a specific static head it exists. So, this particular value is a static head, and then the behavior of the curve, system curve, it looks like in this point, and then when we are plotting the pump performance curve, and there is a point where it crosses or it meets, this point is a pump operating point. So, the combination at which pump is operating is the pump operating point, and brake power efficiency required net positive suction head for the pump can be obtained once operating point has been determined. So, a system curve, that is HQ requirement, is important for any irrigation system. So, the point of intersection, this is what we are putting it here, the point of intersection of HQ curve of pump characteristics and system curve is called pump operating point. So, system curves are constructed by computing the heads required by the irrigation system to deliver different volumes of water per unit of time. It is computed by using this equation, where we can say the total system head is equal to the suction side lift, the plus the delivery side lift, plus the drawdown in the well, plus the head loss due to friction in the pipe system. Then ML refers to the minor losses, plus operating head. Operating head means when there is some device, we need that device to operate. So, operating head requirement, say when we have a sprinkler system which is located at a far off distance place, and then this requires at least say 2.5 kg centimeter square of pressure head, that is, or we can say 25 meter of water. So, to operate that sprinkler, that operating head 25 meter we need to give, plus velocity head. So, all these make the total system head. Now, when we are finalizing the pump performance curve, so one need to draw all the performance characteristics curve. So, foremost thing which I discussed, the first we need to draw the head capacity curve or drawdown capacity curve for the well. So, this is the head capacity curve for the well, and then the pump parameters are head capacity for the pump, then the another parameter is overall efficiency curve, and the other parameter is brake horsepower versus capacity curve. So, horsepower, efficiency, these parts are shown here in this side of the means ordinate, and head is shown on this side of the ordinate. So, when we are plotting the curves, what we are seeing, that what is the appropriate size. So, we see here this is the point of intersection, and at this point of intersection the what we observe here, this is the point where we are getting the efficiency, which is which you can see here, it is about 60%, and corresponding to this is the head, that is a drawdown in the well, and then brake horsepower can be chosen from this point. So, this pump will the pump which will be delivering the discharge of 1800 liter about means 1900, we can say 1900 liter per minute. The corresponding values of the head, drawdown, efficiency, they can be obtained, and accordingly the pump can be selected for a given set of conditions. Now, there are some power requirement estimation. So, these terms are associated. Let us try to know what are those terms. So, to determine horsepower of electric motor or engine, these are the drive which gives to the pump. So, it could be electrical motor or engine driven pump used in driving the pump. It is necessary to know efficiency of the pump, type of drive, type of power unit, head under which the pump operates, and then losses in the piping. So, water horsepower of a pump is given by discharge in liter per second multiplied by total head divided by 76. Now, shaft horsepower is given by water horsepower divided by pump efficiency. So, normally pump efficiency, it is in the order of 60 to 65%. A very good pump, hardly you get 70% efficiency. Now, the drive efficiency is another. So, we should see that there is a minimum loss due to the drive. Sometime we are connecting several belts, and the gear arrangement that reduces the that increases the power brake horsepower requirement. So, this is computed by shaft horsepower divided by drive of efficiency. So, when we are converting the kilowatt input to the electric motor, so brake horsepower multiplied by 0.746 divided by motor efficiency. So, we will get input electric motor power in kilowatt, that can be explained. Pump efficiency, it is the water horsepower divided by shaft horsepower. For direct driven pump, drive efficiency is 100%. So, BHP equal to shaft horsepower. So, we for this lecture you can refer these books and also some other books. So, let us summarize the whole lecture. We discussed about the variable displacement pump and affinity laws. We discussed about the parameters of pumps and centrifugal pump in detail, selection of pump using characteristics curve in detail we had discussion, and then in forthcoming lecture we will discuss about irrigation water quality. So, thank you very much. Good day.